Hey everyone, excited to be here with my awesome teammates from Group 9 in SMJP4213 Modeling and Simulation, Section 2. We're here to chat about our project called Modeling and Simulation of Mechanical Systems with Feedback Control. Meet the brains behind it all, Mohammed Harith, Mohammed HAZIQ, NAJMI AINAN, Mohammed AFIQ, and Mohammed AMIN. Now, what's our project about? Picture a basic spring damper mass system. We're starting there. Then, we're jazzing it up by adding an actuator and throwing in feedback control, using something called a PID controller. We've introduced a cool upgrade to our system, a bidirectional actuator. What's it do? Well, it not only shifts the equilibrium position of the mass but also keeps a steady horizontal pulling force at 3 Newton. But wait, there's more. We've got a position sensor in the mix, and we're using feedback control with a PID controller for precise position control. Our project goals are clear. We're diving into open Modelica software to craft a slick graphical model of our spring damper mass system. Let's see how it behaves. We're also building a model for our spanking new control system. The twist: we're comparing how this model behaves with and without position control. Get ready for simulations. We'll run the system through its paces under different conditions and control settings. Let's see how our control system reacts and the application in the real world. In our project, we'll be exploring 2 distinct control systems: the spring damper mass system without an actuator and PID, and the spring damper mass system with an actuator and PID. We're diving into the methodology by configuring parameters in these 2 different cases, aiming to understand and compare the dynamics of each system.
To ensure the correct simulation of the spring damper mass system, it's crucial to set up parameters for each component. The components in focus for parameter configuration include fixed, spring damper, mass, and force step. This meticulous parameter setup ensures the accurate functioning of our simulation.
Similar to the previous system, it's crucial to set parameters for each component in the PID system to ensure correct simulation. The involved components are force, limiter, gain, PID, constant, feedback, position sensor, and the essential settings of stop time and the number of intervals. We determined the number of cycles by dividing the stop time by the period, resulting in 15.92 cycles for our assignment with a stop time of 1000 and a period of 2 pi. For this assignment, we chose 500 as the number of intervals, ensuring a robust simulation. Based on the parameters set for the spring damper mass system, the results are shown below, which includes the system's behavior with and without control implementation. From this graph, it indicates a steady state at 128 seconds, with the system showing a decay in amplitude over time. Initial 30 seconds display oscillatory behavior, each cycle diminishing in amplitude until reaching equilibrium due to damping force. Energy dissipation is absent during motion. The spring constant is directly proportional to the mass, and damping force is directly proportional to the velocity, both opposing the mass movement. With a PID controller, the system autonomously adjusts to its chosen input. Various parameters are added to observe system behavior under PID control settings. The position sensor measures object position, providing feedback to the system. As force reaches maximum amplitude for steady state, the position sensor detects load changes, proportionally adjusting the feedback signal to regulate the model's behavior.
In the first scenario, where the gain, K, is set to 10, the PID-controlled spring damper mass system achieves a steady state at 4 meters in 77.8 seconds, as indicated by the graph. When the gain is increased to 100 in the second case, the control system reaches a steady state at the same 4-meter position much faster, specifically in 21.8 seconds, according to the graph. In the third case, with a higher gain of 1000, the system takes 26.6 seconds to reach a steady state at 4 meters, as observed from the corresponding graph. For real-world application nowadays, tuned mass dampers, TMD, in tall buildings combat wind-induced vibrations, preventing swaying and structural compromise. Wind forces can cause discomfort and significant movement, exceeding 1 meter at the top. TMD systems, often large concrete or steel structures, absorb and dissipate energy by countering vibrations at the building's resonance frequency. Tuned to the natural frequency, they efficiently mitigate wind-induced vibrations, optimizing structural stability. In summary, OpenModelica enabled effective simulations and modeling of the spring damper mass system. Adding feedback control with a position sensor and PID controller resulted in an efficient system. Despite parameter changes, consistent maximum forces were observed during varied times to reach steady state at 4 m. The optimal setup achieved steady state in 21.8 seconds with a PID controller, K = 100 = 1 = 1. Applied to mitigate wind-induced vibrations in tall buildings, it highlights the impact of PID controller stability on structures using tuned mass dampers, TMD.